Another continuous distribution you need to know is a continuous uniform distribution, or simply a uniform distribution. So they say that a random variable has a uniform distribution on the interval from A to B if it equally likely can take any value in this interval and cannot take values outside of this interval. So it can take values only that are values that are inside this interval, that belong to this interval, and inside all values are equally likely. So the symbol for uniform distribution is letter U, the first letter of the word uniform, and its PDF is a function that is constant between A and B, so it is equal to 1 over B minus A inside this interval and 0 outside of it. And its CDF is a linear function between A and B, so it is 0 when its argument is less than A, 1 when it's more than B, and it is a linear function connecting 0 and 1 between A and B. Expected value is the middle point of this interval, so A plus B over 2, and variance is B minus A squared divided by 12. So where this distribution can be found in our real life? So, actually, its applications in our real life are very rare. So, probably almost the only one is a situation when you are interested in waiting time for a kind of an event, but not in a Poisson series of events, but in such a series that intervals between the events are fixed. For example, you have an ideal bus line where buses depart from the bus stop every, let's say, 5 minutes. So, and this interval is fixed. So after the one bus departed, you wait 5 minutes, 5 minutes and 0 seconds, and another one departs. And in 5 minutes, the next one, and so on. So, and if you come to a bus stop of this ideal bus line at a random time, so the time you will wait for the bus has uniform distribution. Uniform distribution on the interval from 0 to 5 minutes, to the length of this interval. And another application is the rounding errors. So if you are measuring something with some measuring tool, length or height or I don't know, any physical value, and then you are rounding the results of your measurements, let's say up to an integer number. So a rounding error has also a uniform distributed random variable, because if you are rounding up to an integer number, so this error can take values from -1/2 to +1/2. So if you got, let's say, 1.49999999, you round this to 1. And if you got 1.5, you round this to 2. So this rounding error is between -1/2, -0.5, and +0.5. And it can take, equally likely, it can take any value from this range. And so that is why this is also can be described with the uniform distribution. But the main application of uniform distribution is not our real life, but a computer modeling of some random events, random variables, random functions, and so on. So, for example, you want to make a computer game, and in this game some event is to happen, not always, but with a given probability. So let's say with probability 0.3. So let's say that your character is passing some location, and with probability 0.3 something is to happen, and with probability 0.7 so it is not to happen. How this can be modeled? How to do this? So everything, so problems of this kind are solved just with the uniform distribution. So you are using uniform distribution to solve such a problems. For example, in this case, in my example, you just need one realization of a random variable that has uniform distribution from 0 to 1. And if this number you get is less than 0.3, your event happens. And if it is from 0.3 to 1, the event of interest doesn't happen. So that is how uniform distribution can be used for modeling, for computer modeling of random events. And the same is true for random variables, for different distributions also. So, but this is not the the main focus of our today's lecture. So let's go on, and let's talk about another distribution. So the normal distribution. As you can see, all previous distributions were defined using their physical meaning. But this distribution is defined with a formula, with its PDF. Actually, the more strict mathematical way to define a distribution is to provide its PDF or CDF or PMF. But I prefer usually to define distributions by their physical sense. So to make my students understand, so what is this in our real life? But for normal distributions, unfortunately, it is impossible. So in spite of the fact that this distribution is really very, can be found in very different situations. So it describes a great number of random variables we meet in our real life, but it has no direct physical meaning. So because of its wide application, so for example, height of a random adult man is normally distributed. Measurement error of when we are measuring some physical value with a measuring tool is normally distributed. So difference between, for example, today's exchange rate of dollar and ruble and yesterday's one is normally distributed, and so on. So normal distribution can be found in many different spheres. So it has no direct physical meaning, and that is why I have to so normal distribution has no direct physical meaning, and that is why I have to define it using its PDF. So I have to define it in mathematical way. So you can see the definition. A random variable has a normal distribution with parameters mu and sigma squared if its PDF is equal to the formula you can see. So 1 over square root of 2 pi times sigma times exponent of minus x minus mu squared divided by 2 sigma squared. So the symbol of normal distribution is letter n, and what you should know. These parameters mu and sigma squared are expected value and the variance respectively. And so the PDF is given in the definition itself. And as for the CDF, there are some problems. So the CDF is an integral of the PDF, as you know, but integral of the PDF of the normal distribution cannot be expressed with elementary functions. So elementary functions are the functions you study in secondary school. So polynomial, logarithm, exponent, trigonometrical functions, sinus, cosinus, and so on. So this integral cannot be expressed with elementary functions, and that is why a special table function is used for the PDF, for the CDF of a normal distribution. Sometimes it is called a Laplace function, sometimes it is called simply phi, sometimes it is called normal CDF. So we use capital Greek letter phi to denote this function. And so to find the value of this phi in a given point, you are to use tables. So you can Google for just table of the CDF of the normal distribution, and you will get the table of values of this function. And so for normally distributed random variable, probability to take value from a given range can also be found using this phi. So probability that x will take value from a to b is phi of b minus mu divided by sigma minus phi of a minus mu divided by sigma. So you need to know borders of your interval of interest, you need to know parameters mu and sigma, and you need to have a table of values of this function to find probabilities of this kind. And one more thing you should know about normal distribution. If there are two normally distributed random variables and there is a third random variable that is a linear function of these two, so if z is linear function of x and y are both normally distributed, then z also has normal distribution. This is an important theorem. It is not true for other distributions we discussed today. For example, a linear function of two uniformly distributed, of two exponentially distributed random variables won't have uniform or exponential distribution, but for normal distribution this is true. And so if you see a random variable that is a linear function of one or of two or of several normally distributed random variables, it is also normally distributed. When dealing with normally distributed random variables, the most typical problem is to find the probability that the random variable of our interest will take value from a given interval when the parameters of the distributions are known. So let's solve a problem of this kind. So let's say that there is a measuring tool to measure length and there is a measurement error. So x is a measurement error, and so this measurement error is normally distributed, and we know that there is no systematic error. No systematic error means that mean error, average error is 0, and also the standard deviation of the error is given, and it is equal to 4 micrometers. So we can say that X has normal distribution with parameters 0 and 16. So 16 is 4 squared, as the second parameter is not sigma, not the standard deviation, but the variance, so sigma squared. So, and they ask for two probabilities. Probability that absolute value of X will be more than 6 micrometers, and probability that X will take value from 0.5 to 3.5 micrometers. So let me remind you the general formula. The general formula is that if X has normal distribution with given parameters u and sigma squared, then probability that X is from A to B can be found as phi of B minus mu over sigma minus phi of A minus mu over sigma. So let's apply this to the first probability we were asked to find. So P of modulus X more than 6 is 1 minus probability of the complement event, 1 minus probability that modulus X is less or equal than 6. And now we can open this modulus sign, and this is 1 minus probability that X is from minus 6 to plus 6. Please mind that for continuously distributed random variables, it's no matter if this inequality is strict or not. So equal, so less or equal, it's the same. So probability, it doesn't affect the probability. So we can apply this formula to this expression in spite of the fact that this inequality is not strict. So, okay, according to this formula, this is 1 minus phi of B is 6, mu is 0, and sigma is 4. Minus phi of minus 6 minus 0 divided by 4. Not minus, plus. So 2 minuses give us plus. Okay, so 6 over 4 is 1.5, 1.5. So 1 minus phi of 1.5 plus phi of minus 1.5. So now I open the table. I take the table of values of this function, so table of the phi function, and in the table I can find these values, so values of phi in these 2 points, 1.5 and minus 1.5, and they are respectively 0.9332 and 0.0668. So after I do the necessary calculations, I'll get 0.1336. So this is the first probability. Probability that this error that its absolute value will be more than 6. So now let's find the second probability we were asked to find here. We see that it has the same form as in this expression, so no obstacles to apply this formula directly. Probability that X is between 0.5 and 3.5 is phi of 3.5 minus 0 divided by 4 minus phi of 0.5 minus 0 divided by 4. So, if we divide 3.5 by 4, this is phi of 0.875, and this is 1 over 8, so this is phi of 0.125. So now, if I look at the table of the values of the phi function, I will see that there are no such values as 0.875 there, so only 0.87 and 0.88. And for this also only 0.12 and 0.13. So what should I do in such a situation? So the best way to solve this problem is to take both values for phi of 0.87 and phi of 0.88 and take their average. So add them and divide the sum by 2. And so average value is approximately what you need. So if I do so, I'll get that this is approximately 0.809 and this is approximately 0.549. So the only step is to subtract one from the other, and so we will get 0.26. And this is the probability that x will take value from this interval.